Welcome to the review video cast on Chapter 16, Acids and Bases. Make sure you have a piece of paper and pencil out. And you're able to write down the notes during the chapter. Pause the video now if you need to get those things. All right, acids and bases. Way back when, the first time that acids and bases were defined as a source of OH minus ions, and acids were defined as a source of H plus ions. H plus ions were then further discovered to be composed of a proton in the nucleus and then one electron on the outside. When this electron was removed, the only thing that remained was this proton, and therefore things that are H plus are now simply called many times protons, because that's all that's left of the atom. The electron was removed and it's just a proton. This led to a better definition of acids and bases, where we defined acids as proton donors, acids as proton donors, and bases as proton acceptors. Bases are H plus acceptors, acids are H plus donors. Keep that straight in your head. I always remember it like this. There's a big evil looking B base shaped looking guy with big crunchy teeth, and his name is Base Monster, and he eats H pluses because he has a tendency to accept or eat protons. All right? Once you see a reaction, you should be able to identify the acid, the base, the conjugate acid, and the conjugate base. So you have to look from the left side to the right side of the reaction, and you'll notice that HCN becomes CN minus. Therefore, it's a proton donor, and so it is called an acid. HOH right here becomes H3O plus. It accepts a proton, therefore it is known as a base. Conversely, on the other side, you can look actually backwards in the reaction, and you can decide what happens backwards, except we don't call those acids and bases now, we call those the conjugates. And so this would be the conjugate base because it would accept a proton from here to here, and this would be known as the conjugate acid because it is a proton donor. So acid, base, conjugate acid. Be good at identifying those. Now, you should also be able to identify acids, bases, and conjugate bases just by looking at the formula. So, for example, here's a base known as ammonia, NH3. What is the conjugate acid of ammonia? Well, bases are good proton acceptors, and so the conjugate acid would be NH4 with a +1 higher charge. And since it's charged with 0 here, it becomes NH4 positive 1. Okay, here's HPO4 minus, and we're asking what is the conjugate acid of this? So this is acting as a base, and so being a proton acceptor then would mean that it would form H2PO4 and would have a -1 charge instead of -2 because it accepted a proton and therefore went up 1 in charge. You should be able to do the opposite too. HPO4 2 minus obviously has an H in it right here, and if it were to act as an acid, it could donate that proton, and then what's left over would be what's called its conjugate base. So to find the conjugate base, then remove the hydrogen, and what would be left over? Well, PO4, and the charge would have gone from -2 to -3. So PO4 -3 would be the conjugate base. Know your conjugates. Be able to determine what the conjugate acid or the conjugate base is of one or the other very quickly, just by adding and subtracting protons from, and then making sure the charge is right, from different species. All right, let's talk about strongs for a second. There are such things as strong acids and strong bases, and weak acids and weak bases. Strong acids are hyperhickel high, honohickel low, H2SO4. Make sure you've got those memorized, solid. The strong bases are the ones that form a B on the periodic table: lithium, sodium, potassium, rubidium, cesium, calcium, strontium, barium. Noticing that the group 2 cations right here form 2 OHs. Notice it's 2. This forms a B on the periodic table, and you know how this is shaped right here with calcium, strontium, and barium, and that's like the letter B, and those are the strong bases. Okay? Well, there's confusion as to what the word strong means, and a lot of people, think that strong means it reacts a lot. Well, that could be true, but it's not necessarily true. It's just because something is strong does not mean how reactive it is. It means how much it dissociates. And there are other words that sound like dissociation, and so it gets really confusing. So here's where the confusion comes in. A lot of people think that dissolve also means dissociate. I'm here to tell you that they are not one and the same. They are not one and the same. Dissolving means that it will go into a substance, like, for example, water, which is what we use a lot, and it will form a homogeneous mixture. It'll be like country time lemonade mix in water. It will be like taking salt and dissolving it into water, okay? Lots of things do this, but not all of them dissociate, okay? Lots of things do this, but not all of them dissociate. So what does dissociate mean? Well, there's about 5 different words that mean dissociate. Dissociates, words that mean the same thing are ionize, divorce, break apart, separate. Strong things do this. Strong things completely dissociate or ionize or divorce or break apart. I think the best word to describe this besides dissociate is ionize, because these things, these strong things right here, when dissolved in water, fully form their ions. Fully form their ions. Here's an example down here. KOH, a strong base, when it dissolves in water, will fully form K plus and OH minus, meaning that the equilibrium constant for this reaction, which would be K plus times OH minus divided by KOH, because these are all aqueous things, would be a really huge number. It would be like 1,000 or 10,000 or something like that, because all of it would become this, and there would be none of this left. So really it's actually a misnomer when in a problem or in a textbook they tell you that the concentration of KOH is 0.1 molar. Because really after it dissociates, once the ionizing occurs, there's none of this left, and all of it has been converted into 0.1 molar solution of K plus and 0.1 molar solution of OH minus, because it's a 1-to-1 ratio. This is why you have to be kind of worried about these guys, because when these guys dissociate, remember that for example, barium hydroxide will form Ba++, but it will form 2 OH minuses, okay? So if the concentration of this is 1 molar, it will actually form a 2 molar solution in OH minus, because there's 2 of these. So know your strong bases, know your strong acids, know that they fully dissociate, ionize, divorce, break apart. The other things that do this ionization, divorcing, breaking apart, and ionizing are the other strong electrolytes, which include the soluble ionic salts. These are the things that you memorize the solubility rules for. That's who fits into this category right here. Those 3 things, strong acids, strong bases, and soluble ionic salts. They're the ones that form ions. Okay, well, what about water? What about water? We talk about everything being dissolved in water, but does water itself form any ions? Well, water can actually, on a very, very limited basis, react with itself, and it can form some H3O plus and some OH minus. And when it does this, it's said to auto-ionize. Auto by itself, ionize, okay? This doesn't happen very much, and as a matter of fact, if you write the K expression for this, you'd write products divided by reactants, and of course the reactants are pure liquids, so you don't put them in there. So it's H3O plus times OH minus, and that equals 1 times 10 to the negative 14th, a really small number, because not a lot of these form from pure water. This K is no longer called Kc or Kp, it's called Kw or Kdub for short, because it's the auto-ionization constant for water. And all aqueous solutions usually follow this equation. And if you know the OH minus, you can find the H plus. A solution is said to be neutral when the H plus and OH minus are equal to one another. This happens in just plain old water. Plain old water. One other thing to know too is that this 1 times 10 to the negative 14th is true at 25 degrees Celsius. But remember, the only thing that can change the K value is the temperature. So if we raise the temperature to, say, 40 degrees Celsius, now Kw will equal something else. So, it'll probably be like 5 times 10 to the negative 14th or something like that. I'm not sure exactly what it would be, but know that it will change with temperature. Well, we want to be able to describe acids and bases in terms of their H plus and OH minus ion concentration. And instead of saying 4 times 10 to the negative 5th or something all the time, scientists have developed these P scales, the pH and the POH scale. And if you want to see a bunch of equations for this, they're actually located on your nice periodic table. That has a good little chart that shows how to interconvert between all 4 of these, where OH minus is related to pH right here. pH is related to POH by taking pH plus POH equals 14. pH is related to H plus, and of course H plus is equal to OH minus by using KW. This box right here will allow you to coordinate all of your calculations between them. The tricky part comes in if you don't have a lot of experience, is to know that if you know one of these things, you can know all the rest. So many times you'll get an equation and it'll say, what's the pH? And you won't have pH even given, but you will be able to find the OH minus ion concentration. Oh, from that you could find the POH and then the pH. And moving in between this box is critical. Got to be able to do that really well. Well, you can measure pH a number of different ways. We've used pH meters in here before, in this class to do it before. You can also measure them with things called indicators. Indicators obviously turn a different color depending on whether something is acidic, basic, or neutral. There's a nice little chart in your book that shows some colors of what indicators change, and you'll notice that there's a range of different number of indicators that show different colors depending on what the pH is, all the way from 0 up to 12 for pH. You'll always want to choose an indicator. This has been a question on the exam before. You'll always want to choose an indicator that changes color when the substance changes at a particular pH that you're interested in. So, how do we calculate the pH, POH, H plus, and OH minus from strong substances? Say, for example, we've got calcium hydroxide. Calcium hydroxide dissociates, or divorces, or ionizes, just like this equation says right here. If the calcium hydroxide concentration is 3 times 10 to the negative 2, find the pH, POH, H plus, and OH minus. Well, this is tricky for some people because they don't realize that since this is strong, this is technically a misnomer. There's not a concentration of CaOH2. This is actually the concentration of Ca++, and it's also the concentration of OH minus, except there's a 2 in front of here. So you have to take 2 times 3 times 10 to the negative 2, multiply those together. You actually have a concentration of OH minus of 6 times 10 to the negative 2. And now you can take and move it through the box that we just talked about right here. And we can go from OH to POH to pH and then back up here to H, or you can move the opposite direction too. So you'd take the negative log of 6 times 10 to the negative 2, which, let's see, the negative log of 7 is 0.85, so this is probably like about 0.8, I'm guessing. And then the negative log of negative 2 is approximately 2. So we should have a POH of about 1.2. You can try it on your calculator if you want. And then remember, pH plus POH is equal to 14. If this is 1.2, then my pH would be somewhere in the neighborhood of 12.8 or so. And I could move to get the other one too. But you should be able to move very easily from these concentrations to another. You do the same thing with HBr or any other strong acid, knowing that the H plus ion concentration is the concentration of the acid. It's a 1-to-1 ratio, and since it's a strong, and that's the key word, since it's a strong acid or base, whatever the concentration of that acid or base is, moves right over to its ions. Moves right over to its ions. So know the definition of strong. What about weaks? Yeah, weaks. There are a lot of weak acids and weak bases in the world, and how do you know which ones they are? Well, it's by process of elimination. If you know the strongs, everything else is weak. Here's an example of a weak acid right here, HNO2, reacting with water. forms H3O plus and NO2 minus. But it only forms a little bit of these. Only forms a little bit of these. In other words, if you write the K expression for this, you write it as H3O plus times NO2 minus divided by HNO2, okay? And, you ignore the water because it's pure liquid. And this K would not have much of this, but it would have lots of this. Not much of this, just a small amount. And so you'd end up with some number like 1 times 10 to the negative fourth. And remember, always take your K and write it over 1. You can see that there's a lot more reactants than there are products. That's what it means to be a weak acid or base, is that there is not much of the products formed. It doesn't mean it's not reactive. HF, for example, is a weak acid, hydrofluoric acid, but it's super reactive. But it's still weak. It doesn't ionize or dissociate very much. Okay? You can calculate how much it's ionized by calculating what's called as percent ionization. The percent ionization is equal to the H plus ion concentration at equilibria divided by the original concentration of the acid times 100%. You can always remember that percent means part divided by whole, and in this case, it's the part at equilibrium divided by the initial. You can find the base ion concentration as well, except for now you're not looking at H plus, it's a base, so you're looking at OH minus, okay? Divided by the original concentration of the base. Remember, it's always equilibrium divided by initial. You can remember that because it's alphabetical, A, B, C, D, E, and then I comes later in the alphabet. Okay, anyway, times 100%. You can get those percent ionizations. And usually, weak acids are less than 5% ionized. Sometimes they're a little bit more. So let's go through a problem right here. In example 1, if the pH is equal to 5, find HNO2 if the Ka is equal to this. Well, we have the balanced equation right up here. This is the equilibrium of interest. And as you'll find, once again, going through this chapter, and especially chapter 17, writing the equilibrium of interest is probably the most difficult part of the whole class. Probably the most difficult part of the whole class. And so we have to take our weak acid, HNO2, when in doubt, react it with water unless it's a strong base, and then take and make some, H3O plus and some NO2 minus. And I always recommend writing down the ice table right away and see what you can fill in. Some people jump right away to plus X, minus X, plus X, minus X. Don't do that. See what you can fill in first. Since they tell us the pH is 5, we can use the box right here to move from pH to H plus. Okay, moving from pH to H plus means that my H plus ion concentration is going to be 1 times 10 to the negative fifth. Oh, look at that. I know the equilibrium concentration of H3O plus. And if I look on this side of the reaction, it's a 1-to-1 ratio between H3O plus and NO2 minus. That also would be 1 times 10 to the negative fifth. And if I know the Ka right here, I could fill in this and say, I don't know what the concentration of this is, and I would have lost 1 times 10 to the negative fifth. I would have lost 1 times 10 to the negative fifth, and this would be question mark minus this. I would have started with none, none. I would have gained 1 times 10 to the negative fifth, gained 1 times 10 to the negative fifth, and I filled in that entire table without using an X, really, or saying lost and gained, because I knew the pH. So always look in the question and see if they give you some information to be able to fill in, especially in this equilibrium area to start with. Makes life a lot easier. So now I can write the Ka expression. I'm just going to jump right to the numbers. It would be 1 times 10 to the negative fifth times 1 times 10 to the negative fifth, so that would be it squared, divided by my question mark right here, minus 1 times 10 to the negative fifth. I'm going to ignore this and say this is small compared to the starting concentration. And I'll find out later if that's okay to do or not. And this is equal to 4.5 times e to the negative 4. I could now do the mathematics here to solve for this question mark. Okay? And then if I want to know if my approximation was okay, I can find what's called my percent ionization. And remember, to find my percent ionization, take my ion that I'm interested in, 1 times 10 to the negative fifth, and divide it by the original concentration, which is the thing that I'm finding right here, because that's my original concentration, and then multiply it by 100. And if it turns out to be 5% or less, it's called the 5% rule, then it's okay to make that approximation. If it turns out to be more, then I've got to include this amount that's lost into the equation. Then especially if it's a lose x, gain x type one, then I end up doing a quadratic. There has never been one where the quadratic has to be done on the AP exam, but they have asked you what about the 5% rule, and they've asked, well, why is it okay to ignore this amount right here? You can say because it's small compared to the concentration right here, and the percent ionization is less than 5. That's a good rule of thumb. Well, bases. Bases are good proton acceptors. Bases are good proton acceptors. Here's an example of a good proton acceptor, and you look at this one and you say, yeah, but that's just the carbonate ion. Didn't I memorize the carbonate ion? Yeah, you memorized that a long, long time ago when you did polyatomic ions. But it actually is a really good base, because this thing right here came from a weak acid called H2CO3, and actually it's a diprotic acid that lost 2 hydrogens, so it wants to get back and look like that H2CO3 if it can, and so it yanks a hydrogen away from the water, forming HCO3 and OH minus. Okay, the Kb is actually 1 times 10 to the negative 4th for this, which makes it a decent base, not super strong, but decent, and there's a problem there if it's 0.1 molar, find the pH. Here are some examples of weak bases right here, and you should become familiar with some of these. Notice here's ammonia, NH3. Here are a couple of weird ones, pyridine and hydroxylamine and methylamine. Notice the amines right here all have a nitrogen, a nitrogen, and a nitrogen. Nitrogen-containing things are usually good bases because you'll see they've got this unshared pair of electrons right here. Whenever you see that nitrogen atom that's only got 3 things attached to it, always think, ooh, it could be basic because it'd be a good proton acceptor. Here's a couple other ions that are good bases. Notice the hypochlorite ion. That would be, the conjugate base of hypochlorous acid. The carbonate ion, one we're just talking about right now, and a hydrosulfide ion. Okay? So bases usually come from 2 classifications, and one of the primary ones is from anions of weak acids. So here's a sample problem. Here's the Kb. If it's a 0.1 molar solution, so now from this thing right here, I'd write an ice table. This would be 0.1 molar. There'd be no water. We don't, well, I mean, there'd be water, but we don't care because we don't know what the concentration is. This would be none and none to start with. And now it's a gain x, lose x one. So I'd gain x here, x and x, lose x here, 0.1 minus x, assume that's small. I'd end up with x squared over 0.1 is equal to 1.8 e to the negative 4th. And then I'd have to solve for x, which would give me my OH minus ion concentration. Remember to take the negative log of that to get the POH and then get the pH. That should be an easy schmeezy problem for you. You should cruise through that. So recognize bases, recognizing bases. First of all, amines are bases. Amines, remember, are things that have a nitrogen with an unshared pair of electrons, or, and then this nitrogen is connected to something. Obviously, it's connected to another hydrogen, and it's called ammonia. But if it's connected to a carbon chain, it can still act basic. Anions. Anions are good bases like ClO minus, CO32 minus, HS minus. They came from salts. They usually come from salts. They usually come from salts whose cation came from a strong base and then will do nothing in solution. And we'll talk about salts in a little bit more and remind you of those things. But general rule of thumb is look out for anions that came from weak acids because they're going to act as good bases. There's a relationship between Ks. Ka times Kb is equal to 1 times 10 to the negative 14th. And this comes because we have that relationship in the autoionization of water. This relationship is given on the yellow periodic table, and you should become familiar with where these equations are. I'm going to zoom in on this right here. And in the equilibrium area, you can see that they've got a number of different equations that are super useful for this. First of all, there's the Ka expression, the Kb expression, the Kw expression equals 1 times 10 to the negative 14th at 25 degrees Celsius, and they hide right below it Ka times Kb. Then they've got the pH and POH equation, and pH plus POH equals 14 equation. And then right down here, we'll get to these. These are the Henry Hasselbalch equations that we'll come to later. And then here's the pKa and pKb equations, used very frequently on AP exams. And then down here was the chapter 15 one. But this box right here with equilibria equations should become super familiar for you, and you should be able to find it really quickly. Salts. Let's talk about salts now, ladies and gentlemen. This, I think, challenges some people to the utmost because you've got to be a good recognizer. Bottom line is salt is a product of an acid and a base. Salt is a product of an acid and a base reaction. When you reacted plus an acid plus a base, you get a salt and water. Okay? You can think of the salt as having two parents. One parent came from the anion of an acid, and the other parent is a cation of the base. There are exceptions to this, but this is the most easy way to remember it. Anion acid, they both start with A. Can you remember that? Cation base. Cation came from the base. Okay? If the salt has an anion from a strong acid, it'll do nothing. If the salt contains a cation from a strong base, it will do nothing. So, for example, anions of strong acids would be bromide, chloride, iodide, nitrate, sulfate, I should say sulfate, what should I say? Chlorate, ClO3, ClO4. Okay, those came from the strong acids. These ions will do nothing in solution. They'll spectate. They won't be good proton acceptors. If the cation came from a strong base, so if it's lithium, sodium, potassium, rubidium, strontium, barium, if it's one of those, they're going to do nothing in solution. They're not going to be good at accepting or giving away anything because they came from a strong base. Okay? They don't want to get back to looking like that acid. They don't want to get back to look like that base. But if it came from a weak acid or a weak base, now you got to think. Now you got to think. Okay? So here's some examples. KF. Split it up. K plus and F minus. And ask where did its parents come from? Well, K plus, of course, came from a strong base. So it's going to do nothing in solution. F minus, though, where did it come from? Well, it came from a weak acid known as HF. It wants to get back to look like HF if it can. So it wants to get a hydrogen. What do you call things that want to get hydrogens? Well, you call them bases. So this solution will be basic. This KF solution will be basic because it will want to get hydrogens. NaBrO2. Na, where did it come from? BrO2 minus. Where did it come from? Well, Na came from a strong base, so it'll do nothing. BrO2 minus came from HBrO2. Not on the list of strong acids up here. So it's going to want to get to look like this acid if it can, and therefore it's going to be a good proton acceptor, and so it will be basic. NH4ClO4. Where did the cat and anion come from? Where did they come from? Well, NH4, not sure where that came from. Well, that came from a base called NH3. Oh, that's a weak base called ammonia. ClO4, that came from a strong acid known as perchloric acid, so that's going to do nothing. But what's this going to want to do? Well, it's going to want to get to look like NH3 if it can. So it's going to want to give away its hydrogen if it can. And if you talk about what things want to give away hydrogens, they're called acids. So this will be an acidic solution. It will be an acidic solution because it will give away an H+. FeCl3, I'm going to hold on to this one for just a second, but this one is going to stun you a little bit because Cl-, of course, came from a strong acid, so it'll do nothing. But what about Fe3+? We never said what that would be like. I mean, normally we'd think of that like this. It'd have a proton to give away to be acidic, and as a matter of fact, it is acidic. But we'll talk about why because we need another definition to say why in just a second. Be able to write these reactions. Be able to write these reactions. I think it's the trickiest thing to be able to do. Be able to say, okay, so I've got some carbonate ion in there. Well, what's it going to act like? Well, it's going to act basic, so make sure I react with water. When in doubt, react with water. Make it act basic, and what's it going to get? It's going to get some HCO3 minus and some OH minus. Oh, it's a product of OH. Okay, so now I can find the pH and all that kind of fun stuff from it. Be able to write these reactions. Exceptions and stranges. Well, these are explained by something called Lewis theory. Scientists found that the definition of an H+ donor being an acid and an H+ acceptor being a base were not sufficient enough. And so G. and Lewis came up with another definition of acids and bases, and it fits right along with the normal definition that we have, except that he talked in terms of electrons. And so instead of saying that bases, NH3 right here is a base called ammonia. Instead of saying that bases are good proton acceptors, he said that they are good electron donors. They're good electron donors. And so if something is a positive ion, like let's say iron positive 3, okay, if it's deficient in electrons, it would be what's called a good electron acceptor. And since acids and bases are opposite of one another, guess what this guy would be classified as? Yeah, he'd be classified as a Lewis acid. This would be classified as a Lewis base. Some fit both definitions. Obviously, NH3 can also just be known as a regular Bronsted-Lowry base, but it also fits the Lewis theory. Lewis theory opens up the possibility for a lot of other acids and bases. So let's take a look at a couple of strange ones right here. AlBr3, a salt, is it acidic, basic, or neutral? We'll break it up. We're going to get Al plus 3 and Br minus. Br minus obviously come from a strong acid, so it'll do nothing. But Al positive 3, what is that going to do? Well, Al positive 3 is a little electron deficient, so it's probably a good electron acceptor. Therefore, we could define it as a Lewis acid. Now, aluminum is actually really weird because it can act a couple of different ways, but that's good enough definition for right now. How about this guy, Bf3? Split that guy up? Okay, let's look at it this way. Bf3 is one of the weirdest things on the periodic table because boron is electron deficient. Notice it only has 2, 4, 6 electrons around it. It would love to get some electrons. What things love to get electrons? Lewis acids. And so Bf3 is a Lewis acid in the sense that it's a good electron acceptor. Notice it doesn't fit the normal definition of acids because it doesn't have any hydrogens to donate, but it's a good electron acceptor, therefore it's a Lewis acid. Fe positive 3, we already talked about that one. That would also be a good electron acceptor, and therefore it's categorized as a Lewis electron, Lewis acid, because it's an electron acceptor. Lastly, structure of acids. Why are these things acidic? What in the Lewis electron dot structure makes things be acidic? 3 things. First of all, you got to have a polar bond between hydrogen and the anion, between hydrogen and the anion. It's got to be polar, but not too polar. HCl, polar, but not too polar. HF, really polar, a little bit too polar, and therefore it's considered to be a weak acid. HI, still a strong acid, but not as strong as HCl. Why? Because this is a polar bond, but it's not as polar. This comes down to knowing your trend of electronegativity on the periodic table. And if you look at the periodic table, all you need to remember is that electronegativity increases up and to the right, with the noble gases being omitted. Fluorine's the most electronegative atom on the periodic table. It's the T-Rex. Okay? It eats electrons for supper. Electronegativity, remember, is just a rating scale that tells you how much something wants to join or grab an electron. And remember, these guys over here want to get electrons more than anything else. And if you remember the trend is up and to the right, you can always know which one has the greatest electronegativity. Second thing, electronegativity in oxyacids. Okay? Remember how we talked about more electronegative? You got to have enough, but not too much. Well, in oxyacids, you just can't get enough no matter what. Oxyacids always take on this form. Some nonmetal, I'll call it Y, connected to an oxygen which is connected to a hydrogen. This hydrogen is known as the acidic hydrogen because it's the thing that's given away or given off. Okay? Take this sequence, for example. It's usually written this way, and people don't know that the Lewis electron dot structure is written like this. HClO, HClO2, HClO3, HClO4. And we know that 3 and 4 are strong acids. Okay? Well, why? First of all, look at the Lewis electron dot structure. Notice it's Cl and then an OH. Cl and then an OH. A couple of years ago, there was a question on the AP exam, and people wrote the Lewis electron dot structure as HClO, and they got totally no points. You should know that the O and the H are together because the O is electronegative enough to hold the hydrogen, and then what happens is once you have more electronegativity around the central atom, it will actually pull these electrons further away from the oxygen, allowing it to release this hydrogen more. You'll notice there's not much else electronegative around the chlorine, so this guy's a weak acid. keeps hold of this hydrogen pretty good. This gets a little bit stronger now because you have an oxygen connected to the chlorine, pulling the electrons this way. 2 oxygens connected. Whoa, yeah, this one's strong enough now where the hydrogen can be released pretty easy. And this one's the strongest of them all. It can release the hydrogen very, very easily. So you can see the more electronegative the atoms are around the central atom, the more acidic the substance will be. Okay. Lastly, as far as strength in acids, a resonance in carboxylic acids. A carboxylic acid, like this one, known as acetic acid or ethanoic acid, has some carbons, a C double bond O OH, C double bond O OH. And this part is the part of interest in the molecule right here. We're going to get rid of this hydrogen right here because that's going to be the acidic hydrogen. Okay, what can happen now is this double bond can resonate between this oxygen and this oxygen, setting up more stability in the conjugate base, making it be a little bit stronger or a little bit more acidic. Also, if you have more electronegative atoms around this portion of the molecule, it will be able to pull the electron density a little bit more this way, and it'll be able to release the hydrogen a little bit quicker. So, for example, this molecule right down here that has fluorines all around the carbon would be a little bit stronger acid than just this regular carboxylic acid, because it'd be easier to release that proton because the electrons are pulled more towards the electronegative fluorines. Let's take a look at a couple of problems from past AP exams that use these topics or use these questions. And we'll just look at the questions and look at the answers, and then you can see that, hey, this stuff does show up on the exam. Okay, here's 2009 question 1. 2009 question 1. It says, answer the following questions related to chemistry. Halogen oxyacids. Okay, use the information below. Here's the Ka of HOCl. Notice they wrote it like the Lewis electron dot structure actually is, right? Giving you a big hint. And then HOBr, they wrote it that way too. And then this is 2 times 10 to the negative 8th, 2 times 10 to the negative 9th. Which of the two S's is stronger? How do you know which one's stronger? Well, remember, strength means how much it dissociates. Strength means how much it dissociates. And so for HOCl, if you react it with water, you would get H3O plus and some OCl minus, okay? And then if you wrote the K for this, the K expression would be H3O plus and OCl minus, and then divided by HOCl. Notice it's products divided by reactants. Products divided by reactants. And what we want to know is who has the most of these ions right here. What kind of number are you going to get for K if you have a lot of these ions? Well, you're going to get a larger number, right? Because it's the numerator over here. So you want to look at the K that has a bigger number. You want to look at a K that has a bigger number. The bigger the K, the stronger the acid. So you should pick HOCl. And justifying your answer, HOCl is a stronger acid because its Ka value is greater than the Ka of HOBr. Second question, draw the complete Lewis dot diagram for the acid you identified in part A. Well, there it is, HOCl. Notice how they drew the Lewis dot diagram. They used all dots in there. They didn't use dashes like I did up here. You can use the dashes to represent a shared pair of electrons, or you can use 2 dots in between. That's just fine. Hypoiodous acid has the formula HOI. Predict whether HOI is a stronger acid or weaker acid than the acid you identified in part A. Justify your prediction in terms of chemical bonding. Well, we just talked about this now, okay? We said how oxyacids, HOBr and HOI, many times depended on the electronegativity of this extra atom right here. That's why you need to know the trend of electronegativities on the periodic table. And if you remember on the periodic table, chlorine is up here, then there's bromine, and there's iodine. And electronegativity increases up and to the right. So who's the most electronegative? Chlorine. So that should be the strongest acid. Then the Br one, then the I one. And so let's read their answer, and let's see if we can understand what they say. HOI is a weaker acid than HOCl because the OH bond in HOI is stronger than the OH bond in HOCl. The lower electronegativity, electron drawing ability, of I compared with that of Cl results in an electron density that is higher, hence a bond that is stronger, between the H and the O atoms in HOI compared with the electron density between H and O atoms in HOCl. Do you like those fancy words they used? Electron density. Get good at using that. Lower electronegativity, electron drawing ability. Love those terms. They also talked about it in terms of conjugate bases too. Backside. Write an equation for the reaction that occurs between hypochlorous acid and water. I told you this is the toughest part for some people. So HOCl and HOH, we drew this on the front side already. You should get OCl minus plus H3O plus. A 1.2 molar NaOCl solution is prepared. The hydrolysis reaction occurs. A hydrolysis reaction is when the anion reacts with water. So we've got the OCl minus, and it hydrolyzes. In other words, it reacts with water to form HOCl and OH minus. Okay? Write the equilibrium constant expression for this critter. So we take the products right here, raise them to the first power, divided by the reactant. Don't include the water. Okay? There's the reaction right there, and there's the Ka. Or I'm sorry, this is actually a Kb expression, right? Because it's acting as a base. Calculate the value of the equilibrium constant for the hydrolysis reaction. Well, now you have to look back up at the very beginning of the problem for this, because they do give you the Ka for HOCl. How is that related to OCl minus acting as a base? Well, Ka times Kb, remember, is equal to 1 times 10 to the negative 14th, and so you can use that to find the Kb for OCl minus. Lastly, calculate the OH minus concentration in 1.2 molar NaOCl. Now they want the OH minus ion concentration. This is going to require an ice table with the equation you wrote up above. So they give the ice table here kind of in an unusual order. They do the change, and then they get the equilibrium value right here in terms of x. Solving for x and using the Kb right here, you end up with OH minus being 6.4 times 10 to the negative 4th. Could you do a problem like that? Could you do a problem like that? Hopefully with this review, it gives you a little better chance at it. Next one. 2009 Form B had an acid-base question in Part 1. In this one it said a pure sample, 14.85 gram sample of the base ethylamine is dissolved in distilled water to make 500 milliliters of solution. Calculate the concentration of ethylamine in the solution. Okay? Calculate the molar concentration. So now convert from grams to moles and divide by the liters, and there you end up with your molarity. Great Chapter 4 question. You should be good at that, converting to moles and dividing, using the molarity equals moles divided by liters triangle. Next one, aqueous ethylamine. Now they give you the equation, which makes it a little easier. So they tell you what the products are. And notice it's acting as a base. It's pulling a hydrogen away from water. Write the equilibrium constant expression. Products divided by reactant. Ignore the water. Products, reactant, okay? Of this and this, which is present in the solution at the higher concentration at equilibrium, justify your answer? Good question. Now go back and look at this reaction. Remember we said this is a base. What kind of base? A weak base, right? So is it going to make lots of this stuff, or is it going to make a little bit of this stuff? Which one? Well, it's not going to make very much of this stuff because it's a weak base, so it will make very little of this, so there should be less of this in there. They'll read their answer. C2H5NH2 is present in the solution at a higher concentration at equilibrium. Ethylamine is a weak base, unless it has a small Kb value, therefore only partial dissociation occurs in water. You like that? They use the word partial dissociation. All right? The rest of that problem went on and had some Chapter 17 stuff in it. Maybe we'll come back to it later. Next problem was from 2002, question number 1. Okay? Hypobromous acid is a weak acid that dissociates in water as represented by the equation above. Calculate the H plus value. It has a pH of 4.95. Well, now you just have to be good at moving between pH and H plus, and know that H plus is equal to 1 times 10 to the negative 4.95, which is almost times 10 to the negative fifth, and you'll find out that it's 1.1 times 10 to the negative fifth. Okay, you'll get your calculator on this, and it should be a great, easy question. Write the equilibrium constant expression for the dissociation of HOBr in water. Then calculate the concentration of this in a solution that has an H plus equal to, notice they give you a concentration to put into an ice table. So here's the Ka expression, and then they're going to have you put H plus into the equilibrium constant expression, knowing that H plus and OBr minus are equal to each other. Solve for this critter right here, and you end up with 0.14 molar. Okay? This question in 2002 actually went on and asked a common ion question. We'll talk about more in Chapter 17. Bottom line, folks, there's a ton to know about acids and bases. Know your basics. Know your basics, yeah, your basics and your acidics. Know your electronegativity trend. Know why they act acidic and basic. Be able to find your conjugates quickly, and life will be glorious for you. Have an absolutely wonderful review of acids and bases.